I put a little parenthetical matter in my title because in ion traps, when we think of gate-based or analog quantum simulation, they're really the same thing in my book. Partly because the trapped ion system, it's a fully connected graph, and we use the same controllers, the same optical controllers in our system. It doesn't have to be optical, but that's the most popular way. And it's really a software switch. If you want to do an analog quantum simulation, if you want to do a QAOA, as Eddie spoke earlier, or if you want to do full-on gate-based, it's really a software switch. And you're sensitive to the same errors. Of course, the problem with gates is that the errors can accumulate in a very nasty way, whereas if you're doing an analog simulation, the errors make the physics rich. Obviously, we're in trapped ions, we're opportunists, and we play kind of both sides. So I'm going to talk a little bit on both sides of that divide. But from a very high level, I never plugged in the remote, sorry. From a very high level, I want to talk a little bit about the hardware, the different modes of hardware that are out there. And this comes, if you've seen me talk before, I usually almost always put the slide up there. It's adapted from an almost 10-year-old review article out of Science, and they highlighted the possible hardwares that can be used to build quantum computers. And to tell you how dated it is, they didn't even have neutral atoms listed or photonics. And of course, those are really coming on strong. And don't look at the numbers too carefully. This is a snapshot in time from a few years ago in terms of the performance and so forth. But what I also did is I reorganized the columns. And the ones on the right, you'll recognize as largely solid state substantiations of qubits. And the ones on the left are the AMO type, I would say the natural qubit systems that, you don't fabricate atoms, electrons, or photons. They already exist. The big challenge is assembling them. And I would argue that challenge on the left is really one of engineering. There's always physics when you tie together many natural particles. You get something that's different than the sum of the individual parts, as Phil Anderson taught us a long time ago. But the challenge in many of these platforms is not physics. We're not going to learn much more about the atom itself, the qubit itself. Whereas on the right, we still have a lot to learn about how solid-state qubits can be better made. You could say there's engineering there, but I think there's also a healthy dose of physics needed to be learned on how to make a surface pure, how to make a substrate pure, how to gate electrodes, a quantum dot, or even superconducting systems where there is a T1 and a T2 process that, I wouldn't say they're perfectly understood. Whereas with a well-designed natural quantum system, there is no idle T1 or T2 that's really relevant. It doesn't mean that you can do infinitely long computations. It just means that the errors are largely control errors. They're from fields that we apply to control the system. And that's why I like to steer that field more toward engineering, because the engineering hasn't been done. Not like what we've had with silicon engineering and Moore's law over the last 50 to 60 years. Of course, because I work on the left-hand side here, I'm very optimistic that engineering will happen. We don't really need breakthroughs in physics, let me put it that way. So I'm here to talk about the trapped ion system, and of the three platforms that have been built into systems. And again, this is maybe a controversial slide because it's maybe not relevant to scale. These are the typical bottleneck in a large-scale quantum system is the entangling gate fidelity or error, if you want. And they're just I just took 1 minus f is equal to error. Very naive. But each of these points over time, over the last 30 years or so, each point, well, most of them deal with maybe exactly 2 qubits. So it might not even be relevant when you make the system big. So that's important. But these points do tell you what the state of the art was, and by pushing for the better fidelities, you can maybe understand any fundamental errors that might be in the system. And I guess the one, and these are every point here has a reference. But the one thing I'm super excited about in the trapped ion work is that these last 2 points, they're both from industry, and that tells you something. It tells you that it can be engineered, because what industry is going to bring that academics can't do is engineering. And even though I'm a faculty of engineering, real engineering just doesn't happen at universities, I'm sorry to say. We train engineers, we try to form theories of systems engineering, but you don't build a helicopter at a university, or I would never fly in one that was built at a university. So it's very exciting, and I think it also tells us, I think in both of these, by the way, neither of these is the company I founded. One's Quantinuum, and Dave Hayes will talk a little bit about one of these points next. The other one is Oxford Ionics, doesn't use lasers at all, they use microwaves. But these, we know at least in the laser-based gates, the fundamental error is a little bit lower, not much. So they're actually, we're realizing near fundamental noise limits of these gates. And of course, there are ways, even in the optical gates, to make it lower. The Oxford Ionics work is microwave. The fundamental error, actually, we don't really know what it is, maybe, I don't know. But it gives us hope that we can come on in. Gives us hope that we can maybe scale. And of course, if you want to scale qubits, you better, it needs to scale commensurate with the error rate. If the error rate's going up as you add qubits, that's probably a bad thing. Okay, so here are the trapped ions. This is a picture of a Sandia trap. It's a silicon trap. This thing doesn't look like silicon. It's painted with gold. There are about 100 electrodes on this surface trap, and there's a horizontal notch in there. Yeah, a lot of details here I won't get into. But floating above this chip, under the control of all these potentials on these electrodes, in this case are exactly 80 ytterbium-171 ions. They're all the same isotope of the same element. They're glowing blue because, well, it's actually UV, and the TV puts a false color image of blue, but this is fluorescence from these atoms glowing under the influence of a resonant laser beam. And what's odd about seeing individual atoms, I guess these days it's old hat, but there's nothing else here. This is all done in a vacuum chamber, so there's no air around. There's no surface, there's no solid. These things are just floating in free space from these electric fields. The altitude is 1/10 of a millimeter. The spacing is clearly optically resolvable. It's a few microns. And one very important thing is that the inside each atom is a qubit that is an effective spin 1/2 object that has a hyperfine splitting of this. And it's a pretty good atomic clock. So every one of them is exactly the same. So we don't think of T1 or T2. Both levels are nearly infinitely long-lived. So this is our platform with which we can make complex entangled states using gates or using continuous fields to study many-body physics, basically. I'm going to go a little bit in detail on the background here, and then I'll step out and talk about high-level experiments that have nothing to do with atoms, but have everything to do with many-body physics, quantum computing, and then I'm going to conclude by talking about how we hope to scale above. I mean, 80 is pretty exciting, but it's not that exciting. We really want like 800 or 8,000, or if you want to do full-out error correction, maybe 8 million. We're told. But the scaling really is the challenge in the trapped ion platform, and I do want to spend some time on that later. Okay, ytterbium-171. Why ytterbium-171? Well, one reason is the electronics is very simple. It's a single electron atom. Well, all the other electrons are sort of inner core. They're not excited, so they're kind of frozen out. So the one valence electron is a lot like hydrogen because the nucleus has spin 1/2. And so there's a hyperfine structure. That's the spin of the electron interacting with the spin of the nucleus of 1/2. It's not exactly a proton, but it's the quantum numbers are the same as hydrogen. I told you before, this splitting here, there is a second order Zeeman shift, which these are sometimes called clock levels, the m=0 levels, because it's second order. And so we're not limited by fluctuating magnetic fields as a T2 problem with the qubit. So up, down, 1, 0 is stored in these two levels. But this is the true ground state here, and even this excited state is super long-lived. We don't have it, there is no T1, idle T1. Now the detection, this is something we almost never think about once you set it up. The detection is state-dependent fluorescence. If the atom is in one state in particular, it will glow when we shine light at the right wavelength. There's 9 digits to this wavelength. I didn't write them all. You can buy that kind of a laser. This is something that sort of comes for free in atomic systems anyway, neutrals as well. And this is real data from a long time ago. We get about a photon every microsecond of collected light, even though we don't collect it all. The atom spits out, I don't know, a photon every 20 nanoseconds, and we collect maybe a few percent of those. So this is a distribution. It's a little more than Poissonian, probably because the laser is fluctuating in power, but clearly distinguishable from zero. If the atom's in the other state, this same laser beam is about, let's see, 20 megahertz, it's about 1,000 line widths away. So when you're in this state, it's largely transparent, and you see, indeed it is, 0 clicks and some dark counts, background light. So these two distributions are distinguishable even in a single shot. So it's very easy to get, how many nines do you want? It's the record, I think, is 5 or 6 nines of detection fidelity. You don't need that if you only have 10 qubits, of course. So we only do, this is another theme in my career, only do as much as you need to do and then stop, because it gets hard. Jungsang Kim has used really fancy detectors and high NA collection, and in about 10 microseconds has gotten more than better than 3 nines. So detection, we don't think about it. It's almost free. Now, the coherent operation allows us to put coherence in the qubit and eventually make entangled states. Another nice feature of ytterbium is that for technical reasons, it's nice to be tuned a third of the way between these two P lines. You don't have to do that, but if you do that, there are the differential AC Stark shifts down here are the same. In neutral atom land, they call it the magic wavelength, although it's not super important here because unlike neutral atoms, we don't need the light to hold on to the atom. But nevertheless, when we drive coherent transitions by sending 2 beams whose beat note matches the splitting, that would allow us to flip a single spin coherently. And I guess the punchline is that this magic wavelength is a commodity. 355 nanometers is it's a third harmonic of YAG, which is 1064. You can buy it. It's used for lithography. It's made for a different purpose. Here's the laser. You could buy it. This company makes a few hundred of these a year. It's very well engineered. It works for years and years without any maintenance. The only button is the on button. So this is the kind of laser you really want. If you're trying to engineer a system, you don't want to be inside of a laser frame all day. And I did that for the first half of my career, I would say, inside a laser frame, half of the day. So this is a pulse laser. It's I won't get into the details here, but it produces a frequency comb, and all pairs of comb teeth that are spaced just right will drive a transition. In fact, I see Dave's name right there. I didn't put this in there just for you. But Dave, actually here, a few hundred yards away, Dave was the first to show this, that a pulse laser can be used, this simple laser can be used to drive such a transition. Okay, now let me give you the back of the envelope version of how we make entangling gates. We have the single qubit operations, entangling gates. Now, here we have to recognize that the spins do not interact, they do not interact natively. Even though they have a tiny magnetic moment. They're way far apart. They're many microns apart. So that time scale is probably minutes or hours. So, however, the motion of these ions is, of course, highly coupled. In a linear crystal like this, it's like masses connected by springs. If you move one of them, they all move. So the idea here is to apply a state-dependent force, a real force that pushes the atom around. Now, these lasers are very much like what are used to trap neutral atoms. Not to run gates on just to trap neutral atoms. We have forces. They're called dipole traps, these optical tweezers. Well, we've been using optical tweezers with trapped ions for 30, 40 years already. And here they modulate the trap, and I'll draw on a little cartoon here. If we want to do an entangling gate between, say, these 2 ions, we apply a laser beam that's tuned and it has the right polarization with the right selection rules so that, say, spin up moves up, spin down moves down. There's lots of ways you can do this. So spin up, up, spin down, down. And so now the idea is if both atoms are in state spin up, then they'll move up together. If they're both in spin down, they'll move down together, and their Coulomb interaction doesn't change. But if they're in the odd parity states, up, down, or down, up, they're a little further apart, and that tiny modulation of the Coulomb energy is enough to score a gate. And so here it is, the defect in the Coulomb energy between when you're on the diagonal versus not being on the diagonal. And you see it's a 1 over r cubed with a dipole moment, an effective dipole moment squared. This is a dipole-dipole interaction, as you expect, because we're moving the single charge up and down at the same time in general, if it's in a superposition. So we're engineering little electric dipoles. And again, it's very much like what you hear in neutral atoms, where they make Rydberg states that have a dipole-dipole interaction, very similar to this. Okay. So here the dipole moment is actually huge. You don't have normal electric dipole moments in particles that are that big. But we've displaced this a few, maybe 5 or 10 nanometers, which is big atomically speaking. So we've made a huge dipole. And they're separated by many microns. So it's all, this linearization is a very good approximation because the displacement's tiny compared to the splitting, okay? So when you look in gate language, if you look at the 4 possibilities of these 2 qubits, only the 2 with odd parity states suffer this phase shift due to the energy change. And by setting that phase shift to pi/2, by tuning either the power and or the time and paying attention to the distance between the 2, you have a gate that's as expressive as a C0 gate, fully entangling when accompanied by rotations. So this idea is a generalization. It's basically it was derived from the original Sirac-Zoller model of quantum computing from long ago. But what I showed you is really the Molmer and Sorensen version. It turns out experimentally it's a lot easier to deal with. Now, 2 shortcuts I made in that discussion. One not so obvious, one I think most of you already are wondering about. The one that's not so obvious is that the most natural way to do this state-dependent force is to do the state dependence along the x-axis of the block sphere. That's okay, it's still as expressive. We call them XX gates sometimes. This is an effective icing interaction, and so the gate we use is XX. But there's a continuous parameter in here. It's important. It's not just an XX, pi/2. You can tune that to be anything you want. But the gate's rather slow. Slow compared to what? Well, the gate typically is 10 to a few hundred microseconds, and that's very slow compared to the vibration of the ions. So the second cheat, the one that you probably sort of were wondering about, what about all the other ions? If you pluck one ion in a string, they all know about it, and that's absolutely true. It's like plucking a guitar string. It's very hard to pluck a guitar string and only have the place you plucked be the part that moves. So in fact, there are, with n qubits, there are n normal modes, and they're all at different frequencies because it's a strongly coupled system. And we have to pluck our guitar string in a very complicated way using laser pulse shapes. We calculate the pulse shape, and you can imagine plucking a guitar string such that when you pluck it in these 2 places in a very complicated way, at the end of the day, the guitar string's at rest. But you've enjoyed this dipole-dipole interaction in the meantime. So that's basically what we do. That's what everybody does in trapped ion quantum computing. They use this Molmer gate to couple in that way. Now, the bad news is you have some classical complexity. You have to calculate the laser pulse shape. It doesn't scale too badly. It scales linearly with the number of qubits, the complexity of the plucking. Right? There's only n normal modes you have to deal with in 1D. So that's mild, not so great news, but it's not a killer at all. It's classical also. Classical complexity is pretty easy if you have the controller. The real good news, though, is that when you couple to these long-range modes, you get rid of the 1/r cubed. In other words, the gates are independent of distance. So you're no longer restricted. This is great because you have a fully connected icing model. So you don't have to swap information. The graph of this is really complicated. It's an n-dimensional graph. Okay. So that's the background of how you entangle. Let's see. Okay, what about all those modes? Here's some real data on the transverse. You'll note I can't go back here. Yeah, you'll note the model here. I was talking about transverse motion, and the reason we use transverse motion is that it's higher frequency. You can stuff lots of ions in a line, and of course the axial motion by design is very, very low. That's why they form a line. So we want to work with the higher frequency modes. They're cleaner, easier to cool, easier to make a pure state, and to get these ions localized. So these are the transverse modes of a crystal of 32 ions in a harmonic trap. There are 64 lines here in both the x and y radial directions, and the laser in this case was sensitive to both directions. And the blue and red, these are theory, where we expected the modes to be in megahertz. The period of motion is half a microsecond or a third of a microsecond. Remember, the gates were many times longer than that. So these modes are resolved over the time of a gate. And here's the data, and they actually match 1-to-1. The intensities are a little different, but you see the two series there. And if you want, the Hamiltonian we have here is spin-dependent force when we apply lasers in a certain way. Now, you can see a problem right away. As we keep packing ions in this crystal, the modes get really close together, and so there's always going to be, that's always a bad thing. You can never do quantum mechanics at zero frequency. And if you have modes that aren't resolved, that means there's no interaction. So you don't want to put too many more than 32 in there. I wouldn't want to put 3,200, maybe 100. I mean, but it's really pushing it, I think. More on that later. Well, one real help is actually to change the axial confinement from being harmonic, and you'll notice that the ions are not spaced isotropically because the ones in the middle are squeezed by the trap and the other ion. Okay, but if we trap in a quartic well, which is a first approximation of a square box would give equally spaced ions, I think, well, very close to it. And it turns out a quartic well with a kind of a flat bottom in the middle almost gives you the same thing, nearly equally spaced ions, maybe not the first and last, but the others are really close to equally spaced. And a little bit of a surprise is that the modes are also roughly equally spaced. Anyway, that's a nice thing, so they don't crowd as much. It's a little better way to use bandwidth, I guess, is one way to look at it. And we park our laser sort of detuned from these modes in general. Let me talk a little more about that. So this state-dependent force, how do we do this? Well, in the ytterbium system, to get concrete, that should be a capital delta there. These laser beams are detuned from the excited state, so no scattering up here, 100 terahertz away or something. So when we apply these three colors, so one goes up and the other two come down, but they're not tuned to this spin flip transition. They're tuned to the so-called sidebands. That's what these things are. These are the red and blue sidebands, which I should have noted. The red sidebands are actually almost vanishing because the ions are cold. They're in their ground state. There is no lower sideband. If you're in the ground state, you can't go to -1, except for this center mass mode, which is not, that's a bad mode. That's a hot mode. It's a center mass mode. It couples to noise. The other internal modes do not. Okay, so when you tune two beat notes to be both on the upper and lower sideband, the Hamiltonian is a Jaynes-Cummings type here, so it's an exchange of energy between the spin and the motion. A denotes the bosonic annihilation operator of the mode in question. Now that's the red sideband or the lower sideband, and the upper or blue sideband is the anti-Jaynes-Cummings. And when you add these two together, you get basically sigma x times x, spin-dependent force, state-dependent force. So you get this just by tuning the red and upper and lower sidebands at the same time. This is the Molmer scheme. They really first pointed that out. Now, we also detune from those sidebands because we might not want to drive on resonance. And by detuning from the sidebands, we get a time dependence in the Hamiltonian. And here's where the spin-spin interaction comes out. You can see mathematically. If you have a time-dependent Hamiltonian, to form the evolution operator, you can't just say e to the I ht. You have to do this Magnus expansion, e to the I integral of h dt, and then plus the commutator of h with itself at later times, integrated over both variables, then the third, fourth, and so forth. I'm dwelling on that for a reason, by the way. But when you look at this expression, h does not commute with itself at later times, but it commutes to a C number, because A and A dagger commute to 1. And so you end up with a sigma x type interaction. That's the Molmer gate. And I was spelling that out because it's a quadratic function of the two spin operators, x. And the reason it's quadratic is not because the Coulomb interaction is two-body. I used to think that when I was young. It's because of the algebra of A and A dagger. It commutes to 1. So let's look at, you might remember I mentioned Milburn as an alternative to Molmer-Sorensen. In Milburn's version of the spin-dependent force, these are resonant sideband operations, spin-dependent. So in one mode of phase space, xp, we start here, and the state spin up x goes that way, the state spin down x goes that way. So it's an opposite displacement depending on the state. And then we change the phase of the displacement in the rotating frame of the motion So instead of having a detuned force, which would give circles in phase space, we have these squares. And so the Mulmer-Sorensen or the Milburn version of the Mulmer-Sorensen gate, we basically enclose these loops in phase space in a spin-dependent way, and those loops, the area of those loops give rise to the phase that gives you the Ising interaction. And a good way to see this, if you're up to speed in your quantum optics, is these are just displacement operators in phase space. They're spin-dependent displacement operators. The sign of the argument depends on the spin state. So alpha and beta here, they depend on the spins. So we have 4 displacements. It looks like they add to nothing. They add to the identity operator, right? We displace again, we undisplace again. Should add to 0. But in fact, the displacement operators, they don't commute. You get a phase factor when you switch the order. And so you end up with this phase factor in the end. That's exactly the phase of the Ising gate we're looking for. And it's bilinear in the spin operators. It's XX, because alpha and beta are both linear in X. Okay, and the reason I'm going through this is that a few years ago, we discovered a very simple modification that allows you to have n-body interactions. So I guess they're gates, but they're more like little mini circuits with n bodies. And the trick is to not do a state-dependent force, do a force, we need to enclose phase space, but do a state-dependent squeezing operator. The squeeze operator in a harmonic oscillator is basically strengthening or weakening the harmonic mode, if you want, adding or subtracting from the frequency of it if you want. But it looks complicated. There are 8 operations. You displace, squeeze, displace up, unsqueeze, displace back here, squeeze, displace down, unsqueeze. Again, does nothing overall except that phase factor. And if you look in your quantum optics texts, if you put a displacement, if you sandwich a displacement number between 2 symmetric squeeze operators, you basically get a displacement of a contracted or a dilated space. Contracted or dilated exponentially in the squeeze operator. So this becomes that right there. And now we have what we had over here. We can commute these two, and you end up with simply a phase factor. But the phase factor is exponential in the spin operators, which is all the difference in the world, because now we carry all terms, all n-body operations. If you want to look at it, the algebra of A and B don't matter here, because the squeeze is A squared and A dagger squared. Those operators, they commute, I think, to A dagger A or something. The commutators never stop. So the Magnus expansion never terminates, and so we get n-body interactions that come along with it. In fact, the form of the effective Hamiltonian, I call them polynomials, and we have control over these how many n-body interactions, how many n-1, what's the strength of the n-2, n-3, and so forth. Like I said, these are like mini circuits. And the good news is you don't need much squeezing. If you've ever heard the term squeeze state before, as soon as somebody says, oh, we need 20 or 30 dBs of squeezing, you should leave the room, because it's not going to happen. You're always very sensitive to something behind the scenes. Here, we don't need much squeezing. Just need a dB or something. And the best thing is that this is a software switch. Instead of tuning to the first upper and lower sidebands, we tune to the second upper and lower sidebands, and there's the A squared and A dagger squared. This thing gives you that n-body interaction. And we demonstrated it with just 3 and 4 qubits, showing that we got 3-body dynamics and 4-body dynamics. That's a little less direct here. The GHZ state has a nice witness you can measure right away. But this graph here between the 4 qubits, yeah, there's a 4-body interaction, but there's also 3-body interactions and 2-body interactions. It's complicated. It's a 4-qubit circuit with a bunch of parameters. And so I guess I leave it to you. I mean, this I think cries for machine learning to be able to optimize it for a particular circuit or something. Okay. All right, so let me move on and start to talk about, quantum simulators. One reason they're easier in trapped ions than fully gate-based quantum computers is that the optics is easy. You can see from this picture. You don't have to poke individual atoms with individual laser beams. That's almost over-constrained, right? You get your atoms all lined up, and then you have to get a damn laser beam on each atom. That's a lot of work. It's not impossible. A lot of engineering. In the future, when all that optics is on the chip, it's going to be a lot easier. We're not doing any of that yet. But that engineering is going to really be a boon for trapped ions. Here, we do the same physics, but now we're illuminating all of the ions at the same time with a beat note. And as you might not be surprised, we get an all-to-all icing interaction simultaneously. And it turns out if you go through the math of this icing coupling, it's interesting. It depends on where you tune the lasers compared to all those modes. But by changing that tuning, you can actually tune the range of the icing interaction. In theory, you can tune it roughly goes like 1 over a power law. Although there's for finite numbers, it almost doesn't matter, but the exact formula really has an exponential as well. And in theory, we can tune from a uniform interaction between all pairs to a 1 over r cubed effective interaction. I'm looking at Alexei over there. He's like the world's expert on these long-range, quasi-long-range, having tunable long-range interactions and all the neat phases of matter that you can simulate. So this is really the workhorse for us when we're doing quantum simulations. And again, I won't go through the details of this, but it has to do with, the coupling between I and J has to do with their participation in all of the modes, and you sum over those modes, and they have their own detunings. So this is a complicated sum to take, but in certain limits, if you tune really far away, you get 1 over r cubed. And if you tune real close to the center mass mode, you get 1 over r to the 0, which you don't want to do because, number one, you're so close to a mode that you're making phonons. And number two, that mode, that center mass mode, is a bad one, remember? It gets hot. So it's best to be, the sweet spot is sort of between 1/2 and 2. 1 over r to the 1/2 or 1 over r squared. Okay. Now, there's the icing interaction. It's almost trivial to apply a field, an effective field that's transverse to the icing direction. And you'll note here, I added a beat note right on the so-called carrier. It just flips a spin. And so by doing all 3 of these tones, we have a transverse icing model, which is sort of interesting, obviously, because these 2 parts of the Hamiltonian don't commute, and we can start to study kind of order and things like that. By the way, the phase of this tone allows you to control anywhere in the XY plane of the Bloch sphere. If you apply the same phase as the other beat notes, because of that I right there from e to the ikx, you get a 90-degree phase lag. But if you apply a pi over 2 phase shift on this, you have a longitudinal field. To get a BZ field, that's even easier. To get a BZ field, we simply unbalance these 2 detunings. Okay. As you know, a detuning in a Hamiltonian is sort of like a Z field. Okay, so let's get into the lab. And Dave, this is taking a couple years after you left. This is where Dave Hayes did his thesis. Again, a couple hundred yards away in the old CSS building. And this is really the problem. I mean, if you're wondering why Google and IBM didn't jump into trapped ion business early on, this is probably why. They were scared, scared out of their mind to even try this. I mean, this apparatus only trapped a couple of ions. It wasn't even a big system that had a bunch of beams focusing. So there's a lot of fixed cost to just getting the laser system up. And being in a physics lab, every mirror has all the flexibility that you don't want. You can design experiments. That's great. But if you know what you're doing, you don't need to have all that flexibility. And over the course of the last several years, we've built several systems, and this was the first one. It was built at Maryland, but we moved it to Duke several years ago. Almost everything you saw on that last slide is inside that box. There's a vacuum chamber with the chip, and this one does have 32 beams that focus on individual atoms. We can hold more qubits, but we can only address 32 of them. And this is really, this was a big step in university engineering, should I say. It was funded largely by IARPA in the early days, and NSF and DOE, the NQI centers sort of have funded it since then. But this system, the funding, I mean, it was super expensive to work with. Not Sandia, they're a national lab already, but L3 Harris, they built a lot of our optics. Coherent built that laser I showed you. Companies like AOSense, Cold Quanta building a vacuum system. In that example, Jungsang Kim worked with Cold Quanta to make a vacuum chamber really small. And and you can see it's sealed right on the chip itself. This packaging works really well. So with that system, we can start to move away from atomic physics and even move away from physics and start to think about making programmable quantum states. And this NSF program is called STACK because we sort of have an opportunity to do research on the quantum stack. And again, the atomic physics is way down here, the qubit hardware. At the very top are people that are interested in algorithms or testing new circuits and so forth. But they need to talk to us. We have laser pulses. They need to first translate their circuit into from say C naughts to XX gates. That's kind of an easy one, but it's different. It's more expressible. It has more expression because we have a continuous variable. We can apply an XX for any amount of time. So every gate we do is already analog in a way. But then there's a lot of compiling tricks that can compress that circuit because XXs are more expressive and we have full connectivity and so forth. So we don't have to worry about absolute space in these systems. And then we have to take the gates that we want and make the laser pulses. Remember I told you about all that calibration, making very special laser pulses. So this was, we started this research probably about 2018, realizing that we weren't doing atomic physics anymore. Maybe tweaking things up in the morning, but we were doing things that were quite removed from atomic physics. As we started seeing the challenges, to me, the hardest stuff's in the middle. Well, I guess the hardest stuff's up here. We need to find something useful and that will commercially pay the way. That'll rain dollars on all of us in the university setting to do more research, just like what happened in silicon. Actually, when you think about it, there's so many academics say, well, we don't want, if the companies do really well, it's going to freeze us all out. We won't have any money. But in the 1960s, electrical engineering departments were doing power transfer, transmission lines, Smith charts. And in the 70s, what were they doing? They were doing semiconductor physics, or at least half of all ECS departments were doing semiconductors. So it was a growth area for them. And I think when we have commercial success in this field, it's going to be a huge growth area for physics and CS departments at every university. Okay, so we started realizing that that life was greater than just atomic physics or whatever physics is of your qubit is made of. As an example of the trickiness of a compiler or how you co-design a particular hardware to a particular algorithm, this is just one example. It comes from Ken Brown. In VQE, in variational circuits, you might do something like this with just 2 qubits. Of course, it's extendable to many qubits. You might do a C naught gate, then a tiny rotation, then another full C naught gate. You're moving along the landscape just a tiny bit. That's the variational part. Well, it turns out this circuit is equivalent to that circuit. And in ion traps, this circuit is much cheaper, much higher quality, and much faster. Everything's great about it. And we get a factor of 10 or more in compressing using this. And the reason is, the single bit rotations are free and fast. The errors are parts per million in some cases, and they're very fast. It's the 2 qubit gates that are the problem. We have full C naughts here. That's really expensive. Here we made the small angle in the 2 qubit gate, which is expensive and full of errors. So by making a tiny argument there in the rotation of the icing gate, this is much better. We have full rotations, but again, those are cheap. This is just one example, and there's a lot of heuristics on how to make a circuit work better for the hardware you have. So in the spirit of this conference, we certainly played around a lot with quantum simulations, along with doing quantum circuits, and these go back a long time. But all kinds of different, mostly condensed matter models, lots of collaborations. I think that's the one great thing about building that system is that our collaborations just hit the roof. Mostly theorists, just from everywhere. And I'm not going to talk about all these. I'll maybe only talk about one of them, partly because I don't want to steal Alexei's fire. He had a huge hand, along with Zori Davuti, who she said she left the room halfway, but she wasn't protesting. She had something else to do. But the groups of Alexei and Zori it's been wonderful, the collaborations here, and many others. And I think Alexei will talk a little bit about using this type of a system to simulate meson scattering, string breaking, 1D phase transitions, things like this. I see Elizabeth in the crowd back there. Paper's coming out soon, right? Okay, very good, very good. But I will talk about one of them. Actually, well, I'm running out of time. Let me talk. You've seen this one. This is actually from several years ago, but it has to do with something called a dynamical phase transition. And let me quickly go through this. The idea here is we have what I like about this experiment. This is one of the simplest experiments we could do. We prepare all the spins along the x direction. We apply, we quench, we turn this on very fast compared to any other time scales. And it's a transverse Ising model, the one we know and love. And this, I don't know, alpha is maybe 1.5 or something like that. And then we measure the spins along x. And what we're going to vary is b over j naught. In other words, the effective field, transverse field, compared to the nearest neighbor Ising interaction. And there's obviously a competition here. If b is really small, nothing happens because we're already in an eigenstate of x, so there's no dynamics. If b is very big, it's also kind of trivial. All the spins independently precess along that field. But at intermediate values, you get an interesting transition between those two domains. And so when you measure just the magnetization of these spins, which is the brightness along the x direction, we have a hard pi over 2 plus on all the spins. We measure along z, of course. And when we have different values of b over j, for small values of b over j, not much happens. Again, we're already in an eigenstate of x almost. When b over j is bigger, we see quite different dynamics going on. And everything in between. Now, this isn't exactly a phase transition. You can't call it. It's a very smooth thing. This is only, I think, 12 spins or something like that. But we can measure everything in a single shot. We have access to every single spin. So let's look at the two-body correlators. There's n squared of those. So we normalize that out. And when we measure the average two-body correlator, this time as a function of the number of spins in the chain, and we're varying b over j, we see actually a dip, and then it kind of comes back up. Mean field theory predicts this, so we're already, at intermediate values of b over j, mean field theory doesn't work. And for 53 spins, the dashed line is just a guide to the eye. We can't theoretically describe that. It's a complicated system, big Hilbert space. But again, I wouldn't call that a phase transition. The dip should have a logarithmic divergence at 0 when we get to infinitely many spins, but it really slowly converges to that. But again, we have access to every single spin in a single shot. So we measured a weird order parameter, the size of the largest domain at the end of the day. And we averaged over many realizations. So as we increase b over j, we just look for the longest domain in a single shot. At each point of b over j, we might take 1,000 shots. And as we plot the mean size, the average largest domain size, we see this much sharper dip. The dashed lines are just to guide the eye. There's no theory behind it. But we couldn't calculate. That's not 1, actually. It's a little less. It's statistically significantly less than 1. So we can't calculate what that is. It doesn't mean it's really interesting. This is a pretty weird type of interaction. And so you can't run around claiming quantum supremacy because somebody probably could figure this out. We just didn't know how. Okay. So in terms of circuits, this is an example of an interaction. It took many years to finally run these circuits with Umesh Vazirani, Norm Yao, when he was at Berkeley, and also Thomas Vidic at Caltech. And the idea here is this is sort of a precursor to quantum supremacy. When you get a bigger system, it's a good way to show that you have a quantum computer. It's in the area of certification of a quantum computer. And it doesn't require a quantum computer from the verifier. Okay. Now, so this is like Shor's algorithm. That's like the surefire test of a quantum computer. If you feed me big numbers that you think I can't factor, but I keep factoring them one after another, you must conclude I have a quantum computer, right? I guess there's some high-level assumptions that I'm not a mathematician. I won't worry about those. But that's Shor's algorithm is a great litmus test for testing whether somebody has a quantum computer, and you don't need one to prove it. So this is in stark contrast to any circuit that has random circuits, like quantum volume circuits or the Google quantum supremacy experiment, which when the quantum computer gets interesting, you can't prove it because you can't classically calculate it either. So it sort of has its own obsolescence, that type of a certification. So the point here in these two types of problems is that they both allow you to do what you could do with Shor, but they're significantly easier than Shor. But and we ran circuits on these two applications. Of course, we didn't claim quantum supremacy because these quantum computers are still too small. But let me just concentrate on this one, for instance. This is most of these types of circuits that do this are related to cryptography, one-way functions and so forth. This one-way function is a 2-to-1 function. F of x, it's not a to the x mod n, that would be Shor's algorithm. This is x squared mod n, a lot easier. If you don't know the factors of n, so n's a big number, if you don't know the factors of n, you can't find the colliding inputs that give the same output. Even if I give you one input that gives you, of course, it's easy to find the output for any single input, but you can't find the colliding input. And basically, there's a circuit that says that a quantum circuit that with probability 3/4 can tell you whether the two colliding inputs have the same or different parity. Classically, that probability is 1/2. You just have to guess. It's like guesswork. So there's actually a line between quantum and classical. And so it's kind of interesting. The biggest n I'm kind of embarrassed, the biggest n we use, I think, was 21. So we still have a long ways to go. But you've heard numbers for Shor. To do interesting Shor where n is big, you need maybe, I don't know, 100 million qubits, maybe billions of gates. This is a lot easier. Umesh thinks that maybe with 1,000 qubits and several 100,000 gates. That's significantly easier than Shor. Yeah, okay. Anyway, so let me go really fast. Embarrassingly fast. I do want to talk a little bit about that. Well, in doing that, we had to do a mid-circuit measurement and then a feed forward based on that measurement, which again, it was an application that made us make the experiment a little better. So that was fun. Of course, Dave will talk about a much more fancy version of mid-circuit measurement. Okay, so that was fun. I'll skip over this, and unfortunately, Michael, we've been working very closely with Michael Gouland's on these measurement-induced phase transitions, akin to percolation phase transitions you see. By adding errors randomly, measurements randomly in a circuit, you get a sort of a phase transition in an area versus volume law of the resulting entanglement. A lot of ways to look at that. And again, apologize for moving so fast. Yeah, there's a DARPA program based on this. I would say based on a lot of Michael's work. This last example of a simulation was the simulation of the SSH spin model, which is, if you don't know it, it's basically an alternating kind of alternating hybridization of the Ising model, where you have weak, strong, weak, strong, weak, strong, and we generated it by adding a sinusoidally varying transverse field to this Ising model with a DC transverse field. I won't get into the details, but this was 22 ions. There's actually 27 ions here. We used the central 22 of them. And if you do it, and you can see the modulation of that field is funny. It has pairwise 0, 1, 2, 3, 4, and 5. And so there's a phase boundary every other ion. This is not the interesting one with the strong bond on the opposite, on the ends. We want this one where we have the phase boundary is between 1 and 2 and n minus 1. Here you get the weak bond at the opposite end. So it's an XY model. It does have finite range. It's not a nearest neighbor model. The true SSH is nearest neighbor. But as you might know, the SSH model features an edge state, topological edge state. And we can measure this very directly by putting excitations in the chain, either in the bulk or on the edge. And the vertical axis is time. And as time grows, the coherence in that, this is measured along X, I guess, yeah. The coherence lives for much longer than here. Of course, you have more kind of a diffusion of the excitation in this case, but here it sort of lives longer. It's an indirect, well, I can't say indirect smoking gun, but it's clearly if you have an edge state, you need to show this. I think the next step would be to show coherence between the two edge states. That might take exponentially long though. Okay. Again, lots of other work in the quantum simulation game. Now, I want to, again, briefly go through the scaling, the ways we were going to scale. I say we as the royal we. In the ion trap world, the simplest thing is just to shove more ions in a single trap. In a linear chain, you have limitations. I mentioned the modes sort of collide with each other. Some groups are thinking of making a 2D chain, and there's lots of problems with it, but this picture is from Luming Duan at Tsinghua University. You can see there's a defect here, and the edge is not super smooth, but these defects and these edges are totally repeatable. If you turn the power off and then load another exactly 322 ions, you get exactly that crystal. So it's like a real solid. The defects don't move. Now all he has to do is add optical engineering to this and think about doing quantum computing or quantum simulation. A penning trap is another way. It's a different type of geometry where the ions spin at a few hundred kilohertz. It has its own technical challenges, but they are technical. So that's scaling one. Scaling two, go inside the atom and look for more space. There is a lot of more space inside some atoms. Crystal Senko up at Waterloo has identified and used 24 states in each single atom. Now, she hasn't yet implemented all the gates you need, but she's made measurements of every of those 24 levels with 99.5 fidelity. And the gates are actually extensions of what I already showed you. So there's a lot of room inside the atoms to add. There's a lot of room outside the atoms to add by using the phonon modes, which we only use sort of to mediate the gates. Ken Brown and Jungsang Kim are looking at using the higher order modes, the ones that have short wavelength, high spatial frequency, to actually implement spin boson models. That looks really promising. And you get a huge beef up in the Hilbert space. Instead of just 2 to the n, everything we've done so far, you get to add all the phonon modes up to some truncation level m. So with only 20 ions, if you have 20 modes, each with up to n equals 10, that's a huge Hilbert space. Okay, that's 2. Sorry, I got a couple more. You're looking at me nervously. Okay, scaling 3, I'm not going to talk about this because Dave will. This is, I think Honeywell Quantinuum has really gone furthest in this direction. The idea of shuttling ions, physically moving them between zones, that's sort of an obvious way to scale. It will only go so far, but it will get interestingly far. I think it can go to many hundreds of ions by itself. I think the true long-term modular scaling is use optics. And that is, and this is part of what Dave's thesis was too, so maybe he has these ideas too. The idea of heralding entanglement non-locally between ions that are in different traps. And again, the graph is fully connected. I'm going really fast, I know. The graph is fully connected at scale. There's no other architecture I know of that has that, period, other than optical interconnects. And you can see the PowerPoint version of this is really easy. You just put a bunch of ion traps together and you know, interface them with, this part is easy. It's an optical switch, and those things exist. And you know, I'll skip through the, what I wanted to say is that they're very slow. We actually just set the speed record on this. It's 250 hertz. So it's a very slow operation, but actually we've moved like 6 orders of magnitude almost in the last 15 years. So getting good optical engineering is really going to help that. Now, I wanted to, again, spend just 1 minute on IonQ. Many of you have asked me, what happened to IonQ? Well, nothing happened to IonQ. But I will say that when we published the roadmap on how to make this architecture based on a modular optical interconnect, I got a visit in my office here at Maryland by Harry Weller, who's a venture capitalist with a big venture capital firm. And he said, oh, this is a business plan, and you need to start a company. And of course, I talked to Jungsang Kim, who was down at Duke at the time, and we both said, no, we're doing just fine in the university research. That just got him more hungry. And to make a long story short, over the next couple of years, he eventually seeded us. And then he tragically passed away in the late 2016. So we were kind of left holding the bag without a champion in Silicon Valley. So I had to watch Silicon Valley, the show on HBO. And it's so accurate, it's uncanny. It's really unbelievable. Yeah, I learned how to raise money from VCs. And things just, it was a snowball going down an exponential hill, not down a cliff really. And the company went public in late 2021, as you might know. And its stock is still doing pretty well. It's like a $2 billion market cap or something like that. It's kind of crazy. And they've put their, if you look at between IonQ and Honeywell Quantinuum, that's over $1 billion in private investment in this technology over some number of years. So I'm very proud of just the engineering that can be done with that funding. Now, for better or for worse, there's pressure, especially a public company, to make systems and get them out there, sell them. They put them on these cloud providers, which is a good thing, I think, following IBM's lead to get people to use these machines. But I think a lot of the company was more toward building boxes and selling things instead of looking for R&D in the long haul. And so my departure from IQ was about a year ago, actually. And this very short clip from Silicon Valley, maybe you can kind of identify the characters in there.
We just can't.
I think this thing is dead.
Jack, look, I have no doubt that your guys can sell a box. And an appliance may be a good short-term play, but in the long term, we need to be building our full-time platform.
Gloria, could you call the fish guy and see what kind of warranty we have on these things? I think one of them is dead.
Oh, Jack, please. You said that when we got back from Malian, we would discuss this.
Okay, let's discuss it. Take a look at the conjoined triangles of success. Now, what do those two triangles make together?
A square?
A box. They make a box. You can't make that shit up.
But you literally did make it up.
Yes, I did. And now they teach it at business schools.
Let me conclude by just mentioning that at Duke we have something called the Duke Quantum Center, where we actually have about 6 quantum computers, full stack of different levels of maturity. I showed you one of them already. And we have half theorists, half experimentalists, a good group, young and not so young, different departments. And again, we're interested in the full stack approach to quantum computing at the university, which means we don't have to sell boxes, but we can open up the box and get in there and play around with things like these spin boson models. You can't really do that with any company machine. With that cheap ad for the Duke Quantum Center, I guess I will quit there. Thanks for your patience.
Okay, so we have time for maybe 2 questions.
So you point out there are 3 or 4 different ways to scale, and which one do you think is most promising? And do you think the rest of the problem to scale are just engineering, or there may be fundamental problems to overcome?
Yeah, good question. I think the last one on photonics, I don't really see any other realistic way to get more than 1,000 qubits in any platform, unless you do optical interconnects. Okay, it's not a theorem. You could prove me wrong, but I don't think we need breakthroughs in physics for that to happen. I think there's a lot of engineering that has to happen, and the one we haven't even touched in ions yet is I think I said it is getting that optics on the damn chip, because when somebody slams a door or a train goes by, the chip moves, and the atoms are pegged to the chip. They move with it. So if you get all your optics on that chip, there's no more alignment. And everything's small. Optical systems get better when you make them smaller. And this scaling gets smaller as you make the system bigger in power, bigger in qubits. So I think that's the one thing that we'll have in the long run. Yeah, I mean, if you asked me 15 years ago, I would have said, yeah, 10 years we'll have that stuff. We don't have it yet. But again, nobody's doing that engineering. And that's why I'm glad there are companies out there that are thinking, IonQ, Quantinuum, Oxford Ionics, and other quantum dot companies or neutral atom companies are going to do the same thing. Absolutely, they're going to. So, thanks.
If there are no more questions, let's thank the speaker.